S. The S represents the this kind of numbers, the root, and this is the imaginary. So basically, this is the complex plane of S, and S can be any complex numbers. Okay. So now for the poles here, we represent the poles here is this one is minus zeta omega n, and say this one is omega n times 1 minus zeta squared. Okay. So here we have two poles. One is here, and the other one is symmetric with respect to the real axis. So these are the two poles here. Okay, and usually in control we using cross mark to represent location of the poles. Okay, and don't ask me why, but that is the convention that people get used to do it. So that is the location of the two poles, and from here you can see basically we can connect the two poles, location of the poles to the origin here. Okay, and let me just do one. And so from here you can see if you look at this triangle here. So let me pick up this triangle as the graphical things, and basically for this triangle, let me draw that here. So for this triangle, we have the magnitude here is zeta omega n. This is magnitude. This magnitude is omega n times 1 minus zeta squared. Okay. So here is the theta. So from here you can see cosine theta equal to. So if this is this one, so you can calculate this value is omega n here. Okay. So basically here this magnitude. Are we good? Because this is 90 degrees here. So this one, this side square equal to the square of this plus the square of that one. So you can prove it. So from here you can see the cosine omega n equal to how much? Cosine omega n basically equal to omega n, and zeta omega n equal to zeta. So therefore, this angle here, in particular, this angle is theta, and that is how much is cosine of zeta. You good? Okay, what is zeta again? Zeta is our damping ratio. If you look at your notes, and this zeta is our damping ratio. And for our discussion, zeta is less than 1. If zeta is greater than 1 or equal to 1, the solution process will be different. If you're interested, you can do it by hand. That pretty much will take you a few minutes. You will get it. Okay. If zeta equal to 1 or greater than 1, I can tell you the system response has no oscillations. Okay, just simply decaying, no oscillations. So here we have damping ratio less than 1, then we have oscillations. Then damping ratio less than 1, that means is when zeta is approaching to 1. So for example, when say, if zeta is very small, approaching to 0, then this angle will be big, say 90 degrees. When zeta is very small, say, when zeta is large, say 0.9, then this angle will be small. That means this pole will closer to the real part. Okay, so that is the explanations and in these diagrams, and also showing your handouts there. Okay. The reasons I spent this time a little bit about half hour on this one, because this is very important. This page is very important, have a lot of information. So hopefully you can look over your lecture notes, and hopefully you can integrate the things. So that is the same thing, and let me skip out. So this is another example for you. So let me skip out the calculations. Basically here, for our exercise, we're concerned is about what is the response of the systems. So for example, here we want to know what y of t. So you can do the calculation here. Okay. So transfer functions, we have slightly touched the definitions of the transfer function, but here, for the first time, we can go over the formal definitions. So right now, you see the transfer function basically is a spatial language in controls describing the output relation between the output to input. So basically, this reading is this: output y equal to g times x. Okay, so basically here, if you like, you can put up one. So basically, in terms of writing, is this y equal to g times x. Okay, and here if you like, you can keep the function of x there, but usually for simplicity, we simply y equal to gx. Okay, so consider this example here. So from here, assuming we don't consider the initial conditions, and again, if we don't consider the initial conditions, then basically from here, you know this one basically can be equal to ms squared plus bs plus k times y of s equal to capital X of s. We simply take the Laplace transform of this equation, we obtain this one. Okay, so from here you can see y over s. So in here you can see y over x will be equal to 1 ms squared plus bs plus k. So you simply take the algebraic operations on this one, you obtain this one. Okay, so explicitly that is what I write here. Okay, and for some reasons here I include the initial condition, but sorry, I'm going to modify this one. We look at this one here. Okay, so basically for this case, then you can see for this example, then in particular, our transfer function can be more precise, and that is y, that is x, and y equal to block function, transfer function multiplied with x. So that means this is 1 ms squared plus bs plus k. Okay. So if you wouldn't know the contents of the transfer function yet, you simply use whatever the symbol to represent a gray box. Okay, a gray box can be more detailed as long as you know more information like this one. Okay. So that is the way we do it. And for the transfer functions here, we have a little more the terms. So sometimes we call the input, and sometimes people like to call it excitations. And here I give you certain common names. People like to call it the input, or they call it excitations, excitation, excitation. And some people like to call it command. Okay, so there's a kind of few terms they can exchange. For the output, sometimes people like to call it the response or output, whatever. Okay, and now in general, so here is a spatial the examples like we did here. In general, we have the transfer function gs can be represented by numerators functions and denominator functions. Okay, so just like here, in general, we have the transfer functions can be expressed by this, and we have learned the root of the denominator we call the poles. Okay, so that is one we pick up from the previous example. The other term, the root of the numerators, we call zeros. So here we have two terms here, zeros and poles. Okay? And the characteristic equations simply meaning set q equal to 0. That means denominators polynomial equal to 0. That is called the characteristic equations. Okay, so basically in this page, I kind of give you, for the first time, the official introductions of certain common terms in controls. Okay? Good? And we'll look at more examples here. So again, the transfer functions, and so for example, we look at these transfer functions. Okay, so here the GS equal to this one, and for this one, basically in MATLAB to help you here, I put a command. The command is this. If you like to write the transfer functions, and basically you can do is this. First one, you define your numerator polynomial by whatever the name you give it. Okay, so this meaning the name holders for numerator polynomial, you can whatever the name you give it. And here, this one listed is the coefficients of the polynomial in numerator in descending orders. Okay, 2, 1, 1. Okay, so for example, if you have the functions is s squared plus 1, then basically you have to express it as 2 and 0 in s1 and then 1 in s. So basically this is the second order, first order, and 0 order. If that is 0, I have to put a 0 there. Okay. The same thing denominators. This is a coefficient 1, coefficient 2, coefficient 3, and this is 4. So 1, 2, 3, 4, and common separated by common, or you can separate it by a space. Either way. Okay. Separated by common or space. And then once you have this one, then you use this TF means transfer function. TF is a MATLAB command. And then you simply type TF and using argument of whatever the name you use it. Then this is another system name. So system name, that means the transfer functions. Okay. And on the other side, if you know the transfer function, you can use TF data, then you can extract the numerator and denominators information, vice versa. Okay, so that is the one. This kind of command you can easily, you should be able to easily find them from our textbook. Okay, so this is the kind of the example I quickly show you. Okay, and with a little bit more knowledge and preparation in transfer functions, then we can talk about more. We call the impulse response. Okay. So the transfer functions, basically idea is this. For whatever the input, and here this input right now I change symbol to U. And sometimes people like to use R, X, or U. Okay? And usually the people take C or Y as the output. That is a common term. Okay? So whatever the input we take, then we can have the output. Okay? So for example here, so we consider this function, our example there. So for this example, for that example here is our transfer function and is s, and let me make up one, s squared plus 2s plus 4. Okay, so this corresponding case is omega n equal to the k squared. This is equal to 2. And for this one, 2 zeta omega n, if you remember our previous calculation, equal to this term, equal to 2. So therefore, from here, we can calculate zeta equal to 2 divided by 2 omega n, equal to 1/2. Okay, so for this example, the zeta equal to 0.5, omega n equal to 2. Be good? I just use the numbers for example. So here is our output, and whatever the input, and let me use U. Okay. So now you can see y of s will be equal to s squared plus 2s plus 4 times U of s. Depends on the type of the U, the input that we can calculate the output. So basically the output will be equal to y of t will be equal to Laplace inverse of y of s, right? Okay, now we look at the scenario. For the case 1, let me do this here. Let me do that. So case 1, say the ut equal to delta. What is delta? If you remember, the delta is this is a time, and the delta t is this. We have they call the unit impulse functions. So that means this is just like this. I give the impulse, and impulse happen in no time with a magnitude equal to 1. That's called the impulse. Okay. So this one is we call the impulse. Impulsive input. Impulsive input, or briefly, we just simply call the impulse. Okay, so given to this one, then corresponding, you can see the y of s will be equal to s squared plus 2s plus 4 times us. And what is the corresponding value of the the impulse? So this one corresponding to that equal to 1. The plus transform of the impulse, again, take out your handouts there, and that's equal to 1. So for this case, multiply 1. Be good? Then for this case, are you able to continuously taking Laplace inverse of y to determine the things? That should be okay, right? So can I leave it for your exercise? The same thing, this one basically is this. You can delete it, Laplace inverse of s plus 1 squared plus 3 and 1. Something like this one, and that will be similar to the exercise we're starting from today's. Good? Okay, so I leave that to you because I saw a few people nod your heads. So. Case 2. Say if we have the ut, different input, okay, ut equal to 1. What's this? That is, this is the ut, and that is this one. And this one is called the unit, unit step input. Okay, so this is called the unit step input. So for this one, we have Laplace transform is 1 over s. Okay, and now we see, so therefore y of s will be equal to s squared plus 2s plus 4 times u, and that is 1 over s. Okay, so that means the Laplace transform of the y for this case will be Laplace transform of, say, s and s squared plus 2s plus 4. Let me call the a and b as plus c. So basically for this case, s multiply this one, then we know if we have to factorize into the simple form. You find the coefficient a, b, c first, and then doing the inverse by checking out against the tables. Are we good? Yes or no? Because the majority of the people here have started your homework, so I would dare to do so. Okay, otherwise you can let me know. So really we can continue to play, so we can continue to change the different type of the input that we will obtain the different type of the output. Right? So that is the feature. This is a good sign, the kind of good graphic representations of the system. Everything will be in algebraic, okay, one-to-one mapping. And in this, the following slides, I will in particular focus on the impulse response. Impulse response actually is our case 1. The response to the impulse input, we call the impulse response. Okay, so the impulse response, that means for this case, we know the us, the u of t equal to delta t, and basically that means the u of s equal to 1. Okay, for this case. So now for this case, us equal to 1. So that means for this example from reading this diagram, y will be equal to gs times us, and because us equal to 1, that is gs. Okay? Because this, due to the impulse input, the Laplace transform of if the impulse equal to 1. So basically, after calculation, that equal to gs. Okay, so therefore, our output will be equal to the plus inverse of y. So basically, that simply is the plus inverse of g. Okay? Good? The plus inverse of g, and whatever the g contains, you can simply plug into whatever, and that in terms of symbols, the numeric calculation simply follow this step. Yeah. Good? Okay. And so this is called the impulse response, and this is a result of the impulse response. And however, if the for the other case, if the input is not impulse, rather that is the, say, step input or whatever the input, how can we deal with this one? So the concept follow-up is this. For any kind of the input, we can always visualize this input as the combination of so many numbers of the impulse. So basically, you can see this is, for this example here, let me make a one. So if we have a very general input, so ut, and then we make one. So if this is a very general type of the input functions, so basically from here you can see this is the collections. This is the one impulse at time equal to 0, and this is the second impulse at the t1 and t2 and t3, etc. So you can see as long as we get the limit approaching the duration equal to 0, basically this input can be a combination of so many very close impulse. You can see this kind of generic input can be a continuous firing, a series firing of the impulse continuously. That'd be right. So the concept of how to obtain this output, we simply just added up the impulse response due to this, due to this, due to this, due to this, etc., etc. You good? Okay. Yes? Okay, so if that's good, then we can work on here. So in 6 minutes, I will get that done. So Scott, we can have a new